September 2003. The Hubble Space Telescope is pointed at a patch of sky in the constellation Fornax, a region chosen specifically because it appears to contain almost nothing. No bright stars, no nearby galaxies, no obvious structure. An empty patch, about the size of a grain of sand held at arm's length. For 11 1/3 days, spread across nearly 4 months, Hubble keeps that patch of sky in its sights, collecting faint light, photon by photon, building up an exposure, unlike anything attempted before. 800 separate exposures, taken over 400 orbits of the Earth. When the image is finally assembled and released in March 2004, it does not show emptiness. It shows nearly 10,000 galaxies. Spirals, ellipticals, smudges of light from systems so distant their light has been traveling toward us since not long after the universe itself began. The image is named the Hubble Ultra Deep Field, and it becomes one of the most famous astronomical images ever made, reproduced in textbooks, posters, documentaries, presented for 2 decades as a kind of landmark for what an empty patch of sky actually contains. Roughly 2 decades pass. In the mid-2020s, a different telescope points at that same patch of sky, the James Webb Space Telescope, with an instrument Hubble never had. The mid-infrared instrument, MIRI, capable of seeing wavelengths of light that Hubble's cameras simply cannot detect. Webb spends roughly 41 hours staring at the exact same coordinates Hubble used in 2003-2004. In a single mid-infrared filter, the longest single filter exposure of a distant field Webb has performed to date. Combined with shorter observations in AUR filters, and with existing deep imaging from Webb's near-infrared camera, NIRCam, the total observing time invested in this one patch of sky, across both telescopes and both space observatories, approaches 100 hours. It is worth understanding, even briefly, how MIRI and NIRCam divide the work between them, because this division is central to everything that follows. NIRCam, Webb's primary near-infrared camera, covers wavelengths from roughly 0.6 to 5 microns, overlapping with, and extending somewhat beyond, the red end of what Hubble could see, and forming the backbone of most of Webb's deep field imaging programs, including JWST, the survey that had already imaged this same field extensively before MIDI's. MIRI, by contrast, covers wavelengths from roughly 5 to 28 microns, a range that NIRCam cannot reach at all. The two instruments are not competing to do the same job better or worse. They are, in a real sense, looking at different light entirely, with only a narrow region of overlap around 5 microns where both instruments can detect the same photons. This is why MIDI's specifically chose its primary filter, F560W, at 5.6 microns, just past the edge of NIRCam's reach, in territory that only MIRI can access, while still close enough to NIRCam's longest wavelengths that the two datasets could be meaningfully compared. And in that same patch of sky, the patch astronomers had already photographed for over a week straight, already catalogued, already considered one of the most thoroughly examined regions in the entire observable universe. Webb finds something else. Something that was not in the Hubble image at all. Something that had been sitting there the entire time, invisible, waiting for the right kind of eye. Roughly 500 additional sources, the large majority of them galaxies, and among them, a population of more than 100 objects with a specific, unusual color signature. Unlike anything the original deep field had prepared anyone to expect, this is not a story about a new image of empty space. It is a story about a place we thought we had already finished looking at. The Hubble Ultra Deep Field was not just famous, it was treated, in a real sense, as close to complete, a thorough census of one patch of the early universe, as deep as the technology of its era could make it. When Webb looked again, using light Hubble could never see, it did not just add a little more detail around the edges. It revealed an entire second population of objects hiding in plain sight, a meaningful fraction of them deeply red, looking, at least on first inspection, older and dustier than the simplest expectations for that part of the sky and that era would suggest. This video is about the MIRI Deep Imaging Survey, MIDIS. JWST returned to the Hubble Ultra Deep Field, using roughly 41 hours of observing time in a single mid-infrared filter, the longest single filter exposure of any extragalactic field Webb has performed. Published as a survey paper in 2025. It is about what happens when you take a place that has been photographed, catalogued, and held up as a landmark of human achievement for 2 decades, and look at it again with an instrument sensitive to a part of the light spectrum nobody had been able to use there before. And it is about the roughly 500 sources that survey found, the majority of which are galaxies, and a subset of more than 100 of which show an extremely red color. A signal that, at these distances, usually points toward one of 2 things: a galaxy wrapped in dust, or a galaxy that is, by the standards of the early universe, surprisingly mature. By the end of this video, you will understand what the Hubble Ultra Deep Field actually was and why it mattered. What MIRI can see that Hubble's cameras cannot. What these roughly 500 new sources actually are. And why the specific population of extremely red objects found among them fits into one of the most active and contested conversations in cosmology right now. The question of just how mature the early universe already was. This early. How can a patch of sky that has been stared at for over a week by one of the most powerful telescopes ever built still contain thousands of sources nobody had cleanly detected before? What is different about the wavelengths MIRI observes that allowed it to find an entire hidden population in a field astronomers thought they already knew? What does it mean for a galaxy to look extremely red at these distances, and why are more than 100 of these new objects showing exactly that color? If some of these galaxies turn out to be dustier or more evolved than expected for their distance, does that actually challenge anything about how we think the universe began? Or does it fit into a pattern we are already seeing elsewhere, and what happens next, now that this approach, going back to a place we thought was finished, has worked once? This is not a video claiming the Big Bang has been disproven, or that the universe is somehow older than we think. Nothing in the MIDI's results does that, and any framing that suggests otherwise is overselling what was actually found. This is also not a video that treats this as just another pretty picture from Webb, interesting only as wallpaper. The MIDI's survey is a genuinely significant result, not because of any single object in it, but because of what it demonstrates about how much of the universe remains invisible to us depending entirely on which wavelengths of light we happen to be looking at, even in places we have already studied intensely. The honest version of this story sits between those 2 extremes, and it is, once you understand what was actually found, more interesting than either. Before we continue, if the idea of an already famous, already studied image of the universe turning out to have an entirely separate population of objects hidden inside it is the kind of thing that grabs you, subscribe to Galaxy Pulse. We dig into what THE's results actually say, not just what the headline implies. Now, back to that patch of sky in Fornax. To understand why finding roughly 500 new sources in an already famous field is significant, you need to understand 2 things. What the original Hubble Ultra Deep Field actually represented, and why it was considered, for 2 decades, close to a final W ord for that patch of sky. And what MIRI, the instrument that changed that, can actually see that nothing before it could. The Hubble Ultra Deep Field was the culmination of an idea that had already proven itself once before, with the original Hubble Deep Field in 1995. The logic behind both was the same. If you point a telescope at a patch of sky that appears completely empty, no bright nearby objects, nothing to saturate the detector, and you leave the shutter open for an extremely long time, accumulating light photon by photon, you can detect objects so faint and so far away that no single short exposure could ever reveal them. The reason this technique works at all comes down to a basic property of light detection. A digital camera sensor, whether in a telescope or a phone, works by counting individual photons of light that strike it, building up a signal over time. For a big HT object, like a nearby star, enough photons arrive in a fraction of a second to produce a clear image. For an extremely faint, extremely distant galaxy, perhaps only a handful of photons from that galaxy reach the telescope's mirror in an entire night. A single short exposure would show essentially nothing, just noise, indistinguishable from the galaxy's faint signal. But if you keep the shutter open, or stack together hundreds of separate exposures of the exact same patch of sky, the faint, real signal from the distant galaxy slowly accumulates, image after image, while the random noise in each individual exposure tends to average out. Given enough total exposure time, the signal from even an extraordinarily faint object can rise above the noise and become detectable. This is the entire principle behind every deep field image ever taken. Not a more powerful single snapshot, but the patient accumulation of an enormous number of individually unremarkable snapshots, combined. The ultra-deep field pushed this to its limit for its era. Just over 11 days of total exposure time, broken into 800 individual exposures across 400 orbits, and combined. The chosen patch of sky, in the constellation Fornax, southwest of Orion, was Seal C Ted, specifically because it had almost nothing bright in it, no foreground stars to create glare, no nearby galaxies to dominate the frame, as close to a blank canvas as the sky offers, occupying roughly 1/10 the angular diameter of the full moon. What came back was anything but blank. Nearly 10,000 galaxies, packed into that tiny patch of sky. Galaxies at a huge range of distances, some relatively close, many extremely far. Their light stretched and reddened by the expansion of the universe during its long journey toward us, a phenomenon called redshift, where more distant, more ancient light shifts toward longer, redder wavelengths the further it has traveled through expanding space. The nearest large, well-defined galaxies in the image are seen as they were roughly 1 billion years ago. The smallest, reddest smudges may be among the most distant objects in the frame, dating to within the universe's first billion years. For the following 2 decades, the ultra-deep field became a kind of benchmark. Astronomers used it to study galaxy populations across cosmic time, to test models of how galaxies form and evolve, to estimate how many galaxies exist in a given volume of the early universe. It was revisited, reanalyzed, and combined with data from other telescopes and other surveys, including, eventually, even longer combined exposures that pushed the total integration time on this same patch of sky to over 20 days, in the so-called extreme deep field. But the basic picture, the inventory of what was in that patch of sky, was considered, for all practical purposes, settled. You could refine it. You were not expected to find an entirely new category of object sitting there T-hat the previous surveys had simply missed. It is worth appreciating just how much scientific output came from this one small patch of sky over those 2 decades. The ultra-deep field and its successor images have been used to study how the rate of star formation across the universe has changed over cosmic time, to identify some of the most distant individual galaxies ever confirmed at the time of their discovery, to characterize the strange, irregular shapes of early galaxies before they settled into the familiar spiral and elliptical forms we see in the nearby universe, and to provide one of the key datasets used to estimate how the total number and types of galaxies in the universe have evolved since shortly after the Big Bang. Entire careers were built, in part, on data from this single field. Multiple PhD theses in astronomy departments around the world have used ultra-deep field data as a core component. By any reasonable measure, this was not an under-examined patch of sky. If there was a well-studied category for regions of the observable universe, the Hubble ultra-deep field sat near the very top of it. There is also something fitting, in retrospect, about the choice of constellation. Fornax, Latin for a furnace, was named in the 18th century by the French astronomer Nicolas Louis de Lacaille, after a chemical heating apparatus of the era. As part of a set of constellations he introduced to fill in gaps in the southern sky's star charts, with names drawn from scientific instruments of his time. Nobody, choosing the ultra-deep field's location in 2003, was thinking about the constellation's name as anything other than a convenient, mostly empty patch of southern sky. But there is a kind of unintended resonance in the idea that one of the most productive furnaces of astronomical discovery in the 21st century turned out to sit within a constellation named, by chance, for exactly that kind of apparatus, a place where things are forged, examined, and, as it turns out, occasionally found to contain more than was visible at first glance. All of Hubble's deep field work, including the ultra-deep field, was done primarily in visible and near-infrared light, the range of wavelengths similar to, or just beyond, what the human eye can detect. This is not a limitation born of poor design. It reflects real engineering trade-offs, and it matches the wavelengths at which most relatively nearby, actively star-forming galaxies shine brightest. It is worth understanding why this trade-off exists, because it is the key to the entire MIDI story. Detecting light at longer wavelengths, infrared and beyond, requires detectors that are extremely sensitive to heat, because the detectors themselves, and the telescope structure around them, glow faintly in infrared light, simply by being warm. A camera built to see infrared light has to be cooled, often to extremely low temperatures, or its own thermal glow would overwhelm the faint signal from distant galaxies it is trying to detect. Hubble, launched in 1990 and designed around the technology available at the time, carried instruments capable of some near-infrared observation, but nothing approaching the capability needed to do deep, wide-field imaging far into the mid-infrared. Webb, by contrast, was designed from the outset around this exact problem. Its enormous 5-layer sunshield, roughly the size of a tennis court, keeps the telescope and its instruments passively cooled to extraordinarily low temperatures, and MIRI, Webb's mid-infrared instrument, is cooled even further still, with its own dedicated cryocooler, to operate at a temperature only a few degrees above absolute. This is not an incremental improvement over Hubble's capabilities. It is an entirely different category of instrument, built to access a part of the spectrum that was, for practical purposes, closed to deep extragalactic imaging before Webb existed. This cooling requirement is also part of why Webb operates so differently from Hubble in a practical sense. Hubble orbits the Earth at a relatively low altitude, passing in and out of the Earth's shadow every 90 minutes or so, which is why the ultra-deep field's exposure had to be broken into 800 separate images across 400 orbits. rather than one continuous exposure. Webb, by contrast, operates from a location nearly 1,000,000 miles from Earth, at a gravitationally stable point known as the second Lagrange point, where its sunshield can permanently block sunlight from the Sun, Earth, and Moon all at once, allowing the telescope to maintain its extremely cold operating temperature continuously, without the cyclical heating, a ND cooling Hubble experiences on every orbit. This is part of why a single MIRI exposure on one field can run for tens of hours uninterrupted, in a way that would not have been possible for Hubble even if it had carried an equivalent instrument. Under the normal expectation, going back to the ultra-deep field with a better telescope should mean seeing the same galaxies, but more clearly. Sharper edges, better resolved spiral structure, fainter companions around galaxies already catalogued, perhaps a handful of additional very faint, very distant objects at the extreme edge of detectability, pushing the known redshift frontier slightly further. What actually happened when JWST pointed its mid-infrared instrument at that same patch of sky was not simply an incremental sharpening of the existing picture. It was the appearance of a second population of sources, roughly 500 of them, the overwhelming NG majority being galaxies, many of which had essentially no clear counterpart in the original Hubble images at all. Not faint smudges that Hubble had detected weakly and Webb now resolved better, but sources that, in the wavelengths Hubble used, were actively invisible. And, among this new population, a striking subset stood out. More than 100 sources showing an extremely red color when compared across two of Webb's own instruments. Specifically, a strong difference between their brightness in the near-infrared, captured by Webb's NIR cam at around 3.6 microns, and their brightness in the mid-infrared, captured by MIRI at 5.6 microns, with the mid-infrared brightness more than a magnitude greater. This particular kind of redness, relatively faint in near-infrared, comparatively bright in mid-infrared, is a signature associated with two possible explanations. Either the object is wrapped in a significant amount of dust, which absorbs shorter wavelength light and re-emits it at longer, redder wavelengths, or the JWST contains a relatively evolved stellar population, stars that formed a meaningful time before the moment we are observing them, and have shifted toward emitting more of their light at redder wavelengths than a young, freshly formed population would. Both explanations are, in their own way, notable for objects that may be sitting at some of the higher redshifts probed by the survey, meaning some of the earlier cosmic times we can observe. It is worth noting that this comparison was only possible because of work that had already been done in this field before MIDIs even began. The JWST survey, the JWST Advanced Deep Extragalactic Survey, had, in the years leading up to MIDIs, already used NIR cam to image this same patch of sky to extraordinary depth across multiple near-infrared filters, building up one of the most detailed near-infrared catalogs of the Hubble ultra-deep field region that existed. Without this prior NIR cam dataset already in hand, the MIDIs team would have had no near-infrared brightness to compare their new MIRI measurements against, and the entire red color signature, the very thing that makes this population interesting, would have been impossible to identify. MIDIs, in this sense, was not a survey conducted in isolation. It was the missing piece of a multi-year, multi-instrument campaign on this single patch of sky, where each new dataset became more valuable because of everything that had already been collected before it. The MIDIs survey was carried out as part of the guaranteed time observations allocated to the MIRI European Consortium, the group of institutions that helped build the instrument, led by Göran Erslein and a large international team, and published in the Journal Astronomy and Astrophysics in 2025. The team selected the Hubble Ultra Deep Field specifically because it was already so well studied across other wavelengths, meaning any new detections from MIRI could immediately be cross-referenced against decades of existing data from Hubble, from the Spitzer Space Telescope's infrared camera, and from other JWST surveys of the same region, including the JADE survey conducted with NIR-CAM. This cross-referencing strategy is worth pausing on, because it is part of what makes the MIDI's results trustworthy, rather than merely exciting. When a survey finds something new, one of the first questions any careful researcher asks is whether the new finding might simply be an artifact of the new instrument, a calibration error, a processing glitch, a quirk of how the data was reduced. The way to rule this out is to check whether independent datasets, taken with different instruments at different times, see consistent things. Because the Hubble Ultra Deep Field region had already been imaged by Hubble across multiple filters, by Spitzer in the infrared, and by Webb's own NIR-CAM instrument, as part of the JADE survey. The MIDI's team could check every NIW MIRI detection against this existing multi-wavelength archive, a source that showed up only in the MIRI data, with nothing corresponding in any of these other deep, independent datasets, would be far more suspicious than a source that showed up in MIRI and also had a faint, previously uncatalogued counterpart buried in the noise of the NIR-CAM or Spitzer data. This kind of cross-checking is part of why the team felt confident describing the overwhelming majority of their roughly 500 sources as real, despite working at the very faint end of what the instrument can detect. The core of the observation was a single filter, F560W, centered on a wavelength of 5-6 microns, deep in the mid-infrared, far beyond what Hubble's instruments, or the human eye, can detect. The team chose this specific filter because, given the amount of observing time available, it would produce the deepest image, in terms of detecting the faintest possible sources, of any filter MIRI offers. The team committed roughly 41 hours of observing time to this single filter, in a single pointing, to the team's knowledge, the longest single filter exposure of an extragalactic field Webb has performed. Combined with shorter observations in other MIRI filters, and with existing NIR-CAM imaging of the same field, the total observing time invested approached 100 hours. When the data was processed, the team identified approximately 500 distinct sources in the image. The team noted that a small fraction of these are likely affected by imperfect removal of cosmic ray artifacts in the data, a known technical challenge when working at the very faint end of what an instrument can detect. But the overwhelming majority, the team concluded, are real, distant sources, predominantly galaxies. The cosmic ray issue is worth a brief explanation, because it is a genuinely interesting practical challenge in space-based astronomy that has nothing to do with the distant universe at all. Space is full of high-energy particles, cosmic rays, many of THM, originating from sources within our own galaxy, including the aftermath of ancient supernova explosions. When one of these particles strikes a telescope's detector, it can deposit energy in a way that looks, to the detector, indistinguishable from a bright flash of light. Over a 41-hour exposure, an enormous number of these cosmic ray strikes occur, scattered randomly across the detector. The standard way to deal with this is to take many shorter exposures, rather than one continuous one, and then combine them in a way that identifies and removes pixels affected by a cosmic ray strike in any individual exposure. Since a real astronomical source will appear consistently in the same location across many exposures, while a cosmic ray strike will appear as a O-Ni-time spike in just 1 or 2. This process works extremely well in general, but at the very faintest end of detectability, where a real source might itself appear as only a handful of photons above the noise, it becomes statistically possible for an imperfectly removed cosmic ray artifact to be mistaken for a faint real source, or vice versa. This is simply an inherent limitation of working at the edge of what any instrument can detect, and the MIDI's team's acknowledgement of it is a sign of the kind of careful, appropriately hedged reporting that characterizes the survey as a whole. Many of these sources already had measured redshifts from spectroscopy, precise distance measurements based on the specific wavelengths of light absorbed or emitted by elements within galaxies, available from other surveys of the same field, including SP spectroscopic redshifts reaching as high as around 11 to 13, corresponding to a time when the universe was roughly 350 to 400 million years old. The majority of the well-characterized sources, however, sit at redshifts below 6, meaning galaxies that existed when the universe was already more than 1 billion years old, a relatively well-studied era. Many additional sources had photometric redshifts, distance estimates based on comparing a source's brightness across multiple filters rather than detailed spectroscopy, a less precise but still useful method. Among these, a number were estimated to sit at T redshifts between roughly 6 and 12, an era covering the first roughly 800 million years of the universe's history, one of the most actively studied and most contested periods in modern cosmology. The distinction between these two types of redshift measurement matters for how confidently any individual source's distance can be stated, and it is worth being clear about the trade-off involved. A spectroscopic redshift comes from identifying specific N-aerospectral features, emission or absorption lines from particular atoms or molecules, at wavelengths that can only correspond to one specific redshift, given how those features are known to behave. This makes spectroscopic redshifts highly reliable, but obtaining one requires collecting enough light from a source to resolve these narrow features, which for very faint, very distant galaxies can require long observing times on individual targets. A photometric redshift, by contrast, comes from fitting a source's brightness across several broad filters to a library of model galaxy spectra at different redshifts, and finding which redshift produces the best match. This can be done for every source in an image simultaneously, using the same data already collected for the imaging survey itself. No additional observing time required. But it is inherently less precise, and for unusual sources whose true spectra do not closely resemble the library of models used, a photometric redshift estimate can occasionally be substantially wrong. This is part of why the roughly 25 sources estimated to sit between redshift 6 and 12 in MIDIs are described as candidates rather than confirmed. Their redshifts come from photometry, and confirming them would require the kind of spectroscopic follow-up discussed later in this video. And then there was the red population. More than 100 sources showing the specific NIR/CAM to MIRI color difference associated with dust or evolved stellar populations, found across a range of redshifts within the survey. The survey team's own conclusion, scintillated carefully, was that these colors were suggestive of dusty or old stellar populations at high redshift, and that the survey, overall, surpassed the team's pre-flight expectations for what deep MIRI imaging could reveal. This is the finding, stated as precisely as the data currently allows, not "the universe is older than we thought," not "Hubble was wrong." Something more specific and, in its way, more interesting. in a field of sky that astronomers had examined in exquisite detail for 2 decades using visible and near-infrared light. Switching to mid-infrared light revealed more than 100 sources, at a range of relatively early cosmic times, that look like they should not necessarily be quite this red, this early. Either because some of them are full of dust that formed faster than the simplest expectations, or because some of them contain stellar populations that are more evolved than the age of the universe at that point would seem to comfortably allow, or, as latter context in this video will make clear, because in at least some cases, the red color comes from something else entirely. It is worth pausing here to note how unusual it is, in any field of science, for a single survey to produce 3 genuinely distinct candidate explanations for the same observational signature, all of which remain live possibilities pending further work, and all of which would be individually significant if confirmed. This is part of what makes the MIDI's red population such a productive result, even before any of the follow-up spectroscopy has been completed. A result that could only mean one thing would be, in a sense, less useful. It would simply confirm or deny a single hypothesis. A result that could mean any of 3 different things, each with different implications for our understanding of the early universe, is a result that motivates an entire research program. Source-by-source follow-up, statistical analysis of how the different explanations might be distributed across the sample, and comparison with theoretical models for how often each of these scenarios should occur at these redshifts. The uncertainty itself is not a weakness of the result. It is the reason the result matters. There is a useful analogy here to detective work, of the kind that should be familiar from how this channel approaches other mysteries. A single clue that points to exactly one suspect, with no other possibilities, tends to close a case quickly, and tends, in retrospect, not to have been a very interesting case. A clue that is consistent with 3 different suspects, each with a plausible motive, is the kind of clue that drives the rest of the investigation. It tells you where to look next, what additional evidence would distinguish between the possibilities, and why the case is worth pursuing in the first place. The MIDI's red population is exactly this kind of clue. It does not, on its own, tell us whether the early universe was unexpectedly dusty, unexpectedly mature, or unexpectedly full of small, actively growing black holes. But it tells us, with reasonable confidence, that at least one of these 3 things is true for at least some of these sources, and that is more than enough to justify the considerable amount of follow-up observing time that these sources are likely to receive in the coming years. Let's slow down on a few pieces of this, because the terms involved, redshift, mid-infrared, dusty, old stellar populations, are doing a lot of work, and it is worth being clear about what they mean. First, redshift and cosmic time. When we say a galaxy is at a certain redshift, we are describing how much the wavelength of its light has been stretched by the expansion of the universe during the time that light has been traveling toward us. Higher redshift means the light left that galaxy longer ago, which means we are seeing the galaxy as it was earlier in the universe's history. A galaxy at redshift 11, for instance, is being seen as it existed when the universe was around 400 million years old, out of its current age of about 13.8 billion years, a small fraction of cosmic history. It helps to think of redshift less as a distance and more as a kind of time machine dial. Because light travels at a finite speed, looking at an object that is extremely far away is the same as looking back in time to when that light left its source. A galaxy at redshift 1 is being seen as it was when the universe was roughly half its current age. Light from it has been traveling for around 8 billion years. A galaxy at redshift 6 is being seen as it was when the universe was less than 1 billion years old. Light from it has been traveling for nearly 13 billion years. The relationship between redshift and the age of the universe at the time the light was emitted is not linear. It compresses dramatically at high redshift, because the early universe was expanding from an extremely small, extremely dense state, and small changes in redshift at these extremes correspond to enormous differences in how close to the Big Bang itself we are looking. This is part of why the redshift range covered by middies, from below 1 out to potentially around 12, spans such an enormous range of cosmic conditions within a single survey. It covers everything from galaxies in a relatively mature, settled universe to galaxies that may have existed when the first generations of stars were only just beginning to assemble into recognizable structures. Second, why mid-infrared light matters for distant galaxies specifically. As light travels across these enormous distances, redshift stretches it toward longer wavelengths. Light that was originally emitted as visible, or even ultraviolet, light by a very distant galaxy can, by the time it reaches us, have been stretched all the way into the infrared, or even further, into the mid-infrared. This means that for many distant galaxies, the mid-infrared is not some exotic extra channel. It is where a significant portion of their light actually ends up by the time it arrives at Earth. The MIDIS team noted that MIRI at 5.6 microns gives access to the rest frame near-infrared light of galaxies at redshifts above roughly 4, and to the rest frame visible light of galaxies at redshifts above roughly 9. Hubble's instruments simply could not see far enough into this part of the spectrum to catch much of this light. MIRI can. Third, what makes a source look red in the specific sense used here? This is not about a source's true, intrinsic color, in the way you might picture a red star. It is about comparing how bright a source appears in one of Webb's near-infrared filters versus one of its mid-infrared filters. If a source is much brighter in mid-infrared than in near-infrared, relative to what a typical young, dust-free galaxy at that distance would show, that imbalance is the red signal. There are at least two main physical reasons this can happen. Dust, tiny particles of carbon and silicates produced by earlier generations of stars, absorbs shorter wavelength light efficiently and re-radiates that absorbed energy at longer infrared wavelengths, making a dusty galaxy appear faint in near-infrared but comparatively bright in mid-infrared. Alternatively, a population of stars that is relatively evolved, meaning it formed a meaningful amount of time before the moment we are observing it, tends to be dominated by cooler, red stars compared to a freshly formed population dominated by hot, blue, young stars, and this also shifts a galaxy's light toward the redder, longer wavelength end captured by MIRI relative to NIR-CAM. Fourth, why either explanation is notable at these redshifts specifically. Dust requires earlier generations of stars to have lived, fused heavier elements, and ended their lives, scattering that material into space, all before the dust-rich galaxy we are observing existed. An evolved stellar population requires star formation to have begun, and stars to have aged measurably, within the relatively short time available since the Big Bang at that redshift. Neither of these is impossible. Both require things to have happened somewhat faster, or somewhat earlier, than the simplest versions of galaxy formation models originally assumed. Here is why this connects to something bigger than one survey of one patch of sky. The MIDIS results did not appear in isolation. Over the past several years, JWST has repeatedly found galaxies in the early universe that look more massive, more structured, more chemically enriched, or, in this case, more dusty, and potentially more evolved than the simplest models predicted for their cosmic age. Individually, each of these findings has been met with a mix of genuine surprise and careful caution, because each one, examined closely, tends to involve some combination of measurement, uncertainty, alternative explanations, and the genuine difficulty of measuring properties like mass, age, and dust content, precisely for objects this faint and this far away. It is worth surveying, briefly, a few of the other findings that form this broader pattern, because the MIDI's result does not exist in a vacuum. It joins a list. Early JWST surveys identified candidate galaxies at redshifts above 10 that appeared, in initial estimates, to contain stellar masses comparable to much more massive, much more mature galaxies seen at lower redshifts, galaxies that, if the initial mass estimates held up, would have to form an implausibly large fraction of their final stellar mass in an implausibly short time. In several of these cases, follow-up spectroscopy either confirmed unusual properties or revised the initial estimates substantially, sometimes finding that an object was at a lower redshift than first thought, sometimes finding that its mass had been overestimated due to the presence of an active black hole contributing extra light, and sometimes confirming that the galaxy genuinely was unusually massive for its age. Separately, deep spectroscopic surveys have found galaxies, including some that appear to have already stopped forming new stars, so-called quenched or dead galaxies, at redshifts where the existence of any galaxy old enough to have already exhausted its star-forming phase was, on the simplest models, considered surprising. This back and forth between initial estimate and refined follow-up is not a sign of the field being in disarray. It is exactly what should happen when an instrument capable of detecting fainter, more distant objects than any before it starts returning data faster than the community can fully digest. Each individual candidate gets an initial estimate based on the data available at the time it is first identified, and as more data, particularly spectroscopy, becomes available for that specific object, the estimate gets refined, sometimes upward, sometimes downward. The MIDI's red population is, in this sense, at the very beginning of this same process. A set of candidates identified through imaging, awaiting the spectroscopic follow-up that will refine, conf-RM, or, in some cases, overturn the initial photometric classifications. But the pattern itself, repeated across multiple independent surveys, multiple research teams, and now multiple wavelength ranges, including this mid-infrared population from MIDIs, has become difficult to dismiss as a string of unrelated anomalies. Something about how quickly structure, dust, and more evolved stellar populations appeared in the early universe seems, in at least some cases, to be running ahead of the simplest expectations, even if no single result definitively proves anything has gone ρng with our broader understanding of cosmology. The MIDI's red population is a new data point in this pattern, found through a method, mid-infrared imaging of an already exhaustively studied field, that is itself a kind of test. If a field, this well-studied, could still hide a population like this, what does that imply about every other field that has only been studied in visible and near-infrared light? The MIDI's team's own framing of their results was notably measured. They described the survey as surpassing pre-flight expectations, and they described the red population as suggestive of dusty or old stellar populations, careful, appropriately hedged language. But suggestive is the beginning of an investigation, not the end of one. To go from this color is suggestive of dust or age to this specific source is this old, with this much dust, Formed in this way, requires something the imaging survey alone cannot fully provide: detailed spectroscopy, breaking the light from each of the C sources down into its component wavelengths, to identify the specific chemical and physical fingerprints that can distinguish between a dusty young galaxy, a genuinely evolved one, and, as we will get to, something else entirely. That follow-up work is exactly what comes next, and it connects this single survey of one patch of sky to a much larger question that astronomers across multiple JWST programs have been circling for the past several years. A question about just how mature parts of the early universe already were, at points in cosmic history that, on the simplest models, should barely have had time to make any galaxies at all. To understand what astronomers do next with a population of red, potentially high redshift sources, it helps to walk through the leading explanations more carefully, because distinguishing between them is not a minor technical detail. It changes what these objects actually represent. The first possibility is dust, specifically, dust produced by earlier generations of stars. Stars more massive than the Sun live short, intense lives, fusing elements together in their cores, and when they reach the end of their lives, often in supernova explosions, they scatter newly formed elements, carbon, oxygen, silicon, and others, into the surrounding gas. Over time, some of these elements condense into solid grains, dust. This dust then mixes into the gas clouds from which the next generation of stars forms, and some of it remains distributed throughout a galaxy, absorbing light from the stars within it, and re-emitting that energy as infrared radiation. It is worth being specific about the timescales involved here, because they are central to why this is interesting at high redshift. The most massive stars, the ones primarily responsible for rapidly producing and dispersing heavy elements through supernova explosions, live only a few million years before exploding, a blink of an eye on cosmic timescales. This means that, in principle, a galaxy could begin forming stars, have its most massive stars live and die, and start accumulating a meaningful dust get within just a few tens of millions of years of its first stars igniting. The question is not really whether dust production is fast enough in an absolute sense. It can be, for individual massive stars. The question is whether enough of this process see and happen across enough of a galaxy's gas to produce the kind of dust mass needed to noticeably redden a galaxy's overall light within the total time available since the Big Bang at the redshifts in question. At redshift 8, for example, the universe is only around 600 million years old, meaning even if dust production began essentially as soon as the first stars formed, there would be at most a few hundred million years for a galaxy to build up whatever dust content it has by the time we observe it. Whether that is enough time depends on details of how efficiently star formation proceeds, how much of a galaxy's gas gets cycled through massive stars, and how much of the resulting dust stays within the galaxy, rather than being blown out by the same supernova explosions that produced it. All active areas of research that observations like MIDIs help constrain. For a galaxy to be genuinely dusty in the sense relevant here, requires that at least one earlier generation of stars has already completed its life cycle. At the higher redshifts, where some of these MIDI sources may sit, potentially within the first billion years of the universe, this means star formation needed to begin very early, proceed quickly enough for massive stars to form, live and die, and produce enough dust to leave a detectable signature, all within a window of cosmic time that is short by any standard. The second possibility is an evolved stellar population. A galaxy dominated by stars that are not newly formed, but have existed long enough to evolve away from the hot, blue, short-lived massive stars that dominate a young starburst, toward a population WIth, a redder overall color. The kind of population you would expect in a galaxy that formed most of its stars in an earlier burst and has since been relatively quiescent. The timescale question here is, if anything, even sharper than for dust. For a galaxy's overall light to shift noticeably toward redder colors because of an aging stellar population, you generally need a population of stars with masses comparable to, or some U-hat less than the Sun to have had time to evolve off the hot, blue main sequence, a process that, for Sun-like stars, takes billions of years in isolation, far longer than the age of the universe at these redshifts. However, galaxies do not need their entire stellar population to be this old to show a measurably redder color. Even a substantial population of stars with ages of a few 100 million years, formed in an early burst and then left largely undisturbed while the galaxy's overall star formation rate declined, can shift a galaxy's integrated light meaningfully redward compared to a galaxy still actively forming stars at a high rate. The question that follow-up spectroscopy aims to answer for sources like these is not, are these stars billions of years old? They cannot be, given the age of the universe at these redshifts, but rather, do these galaxies show evidence of having formed a significant fraction of their stars in an earlier burst, followed by a period of reduced star formation, which would itself be a notable finding for galaxies seen this early. For a galaxy at high redshift to show this kind of evolved population requires not just that star formation began early, but that a substantial population of stars had time to age measurably, again within a cosmic timeframe that, on the simplest models, barely allows for galaxies to exist yet, let alone to contain populations old enough to look evolved. Both of these possibilities point in a broadly similar direction. That something about galaxy formation in the first billion years or so of the universe may, in at least some cases, be happening faster or starting earlier than the simplest models predict. Neither possibility, on its own, requires discarding the standard picture of the universe's history, but both add to a growing list of observations, suggesting that the standard picture's account of exactly how quickly the first galaxies assembled themselves, and how quickly they produced the heavy elements, dust, and more evolved stellar populations we are now detecting, needs refinement in places. There is a third possibility, however, and it is not a minor footnote. It is central to how this story has continued to develop since the original MIDI's survey paper. A separate population that JWST has found scattered across multiple deep fields, sometimes called little red dots, compact, extremely red sources at high redshift, has been the subject of intense follow-up study. Spectroscopy on a number of these objects revealed that at least some of them are not dusty or evolved galaxies at all, but galaxies hosting actively accreting black holes, whose emission can also produce red colors through an entirely different physical process. Hot material spiraling into a black hole emits its own strong continuum of light, which, after being redshifted across cosmic distances, can mimic the same kind of red near-infrared to mid-infrared color signature as dust or old stars. It is worth understanding, briefly, why an actively accreting black hole produces this kind of signature, because it is a genuinely different physical mechanism from either dust or starlight, even though it can produce a superficially similar color. When material, typically gas, sometimes the remnants of a disrupted star or a steady inflow from the surrounding galaxy, falls toward a black hole, it does not fall in directly. Conservation of angular momentum causes it to spiral inward, forming a flattened, rotating structure called an accretion disk, Friction and other processes within this disk heat the infalling material to extremely high temperatures, causing it to glow brightly across a wide range of wavelengths, from X-rays through visible light and into the infrared. For a sufficiently small, sufficiently obscured black hole, one whose accretion disk is wrapped in its own surrounding cocoon of gas and dust, which is common in the early universe, when galaxies are still gas-rich. Much of the shorter wavelength light from the disk itself can be absorbed by this surrounding material and re-emitted at longer wavelengths, producing an object that, from the outside, can look remarkably like a small, compact, intensely red source, different in its underlying physics from a dusty star-forming galaxy, but not always trivially different in the handful of broadband colors an imaging survey can measure. This finding is directly relevant to the MIDI's red population. Follow-up work specifically targeting the reddest, most compact sources within the MIDI's field, a deeper sub-region of the survey, sometimes referred to as MIDI's deep, identified a small number of candidates, on the order of half a dozen to 10, showing the most extreme versions of this red color. When researchers fit models to the light from these sources, comparing a standard dusty galaxy template against a template based on the spectrum of a confirmed black hole-dominated little red dot from elsewhere in the JWST dataset, at least one of the MIDI's candidates was better fit by the black hole template than by the dusty galaxy template, with the dusty galaxy fit implying an unusually small stellar mass for a galaxy at that redshift. This does not mean the entire red population from MIDIs is secretly a population of disguised black holes. The original survey identified over 100 red sources across a range of redshifts and brightnesses. The deeper follow-up examined a much smaller, more extreme subset, but it is a clear demonstration of the point made earlier in this video. Red, at these distances, is not a single story. It is a color that at least 3 distinct physical processes, dust, evolved stars, and actively accreting black holes, can all produce, and only detailed, source-by-source follow-up can tell them apart. Some of the MIDI's red population will likely turn out to be dusty star-forming galaxies. Some may turn out to be galaxies with genuinely evolved stellar populations. And at least some, on the evidence so far, may turn out to be something that looks, from the outside, like neither a small, intensely red point of light that is not a galaxy's accumulated starlight at all, but the glow of material falling into a black hole. There is a reason the MIDI's results carry more weight than a similar discovery might in a less familiar patch of sky, and it has to do with what astronomers call completeness. The question of whether a survey has found everything there is to find, down to some specified faintness, in the area it covers. The Hubble ultra-deep field, refined over 20 years and combined with data from other observatories at other wavelengths, including earlier infrared surveys with Hubble's own infrared-capable instruments and with the Spitzer Space Telescope, represent one of the most complete catalogs of any patch of sky in existence. Researchers had used this field as a calibration point, a place where, if your model of the galaxy population predicted a certain number of objects of a certain type, you could check at prediction against what was actually observed, with reasonable confidence that what had been observed was close to everything that could be observed, given the technology available. It is worth dwelling on what completeness actually means in practice, because it is a more subtle concept than it might first appear. No survey is complete in an absolute sense. There is always some object, somewhere, too faint for any given instrument to detect. What astronomers mean by completeness is something more like a statement of confidence down to a specific brightness threshold, in a specific range of wavelengths. Down to this faintness, in this part of the spectrum, we believe we have found essentially everything there is to find. The Spitzer Space Telescope, launched in 2003 and operated for over 15 years before being retired, had already extended the ultra-deep field's wavelength coverage somewhat further into the infrared than Hubble alone could reach, and researchers had incorporated that data into their completeness assessments. Spitzer, however, had a much smaller mirror than Webb, and could not match the combination of sensitivity and resolution that MIRI brings to a field this phi-nt. By the early 2020s, the combined Hubble plus Spitzer dataset for this field represented, by the standards of the time, about as complete a picture as existed for any patch of sky. Not complete in an absolute sense, but complete enough that finding an entirely new population, rather than simply extending the faint end of an already known population, would have been considered unlikely. MIDIS did not just add new sources to this catalog. It revealed that the catalog, however complete it appeared by the standards of visible and near-infrared observations, had been missing an entire population that only becomes visible in the mid-infrared. This is a different kind of finding than discovering one unusually interesting galaxy. It is a finding about the catalog itself, about the limits of what complete meant before this observation, and about how many other supposedly well-studied fields, MIG-HT, have similar hidden populations, waiting in wavelengths nobody has yet been able to access there at comparable depth. This is part of why the MIDIS team described their results as surpassing pre-flight expectations. The instrument performed as designed. What was unexpected was how much new material there was for it to find, in a place that had already received this much attention. Imaging surveys like MIDIS identify candidates. They measure brightness across a handful of filters, and from that, estimate rough properties. Approximate distances through photometric redshifts, approximate colors, approximate classifications into category-wise like dusty or evolved. What they cannot do, on their own, is confirm these classifications with the kind of precision needed to settle a scientific debate. That confirmation comes from spectroscopy, and JWST carries instruments specifically designed for this, principally NIR-SPEC, the near-infrared spectrograph, where an imaging survey measures how bright a source is in a few broad wavelength bands. Spectroscopy spreads a source's light out into a detailed spectrum, revealing specific narrow features, emission and absorption lines, produced by particular elements and molecules, at specific wavelengths that shift in a precisely calculable way depending on the source's redshift. The difference between imaging and spectroscopy is sometimes compared to the difference between looking at a person from across a room and having a detailed conversation with them. From across the room, you can tell roughly how tall someone is, what color their clothes are, whether they appear to be moving quickly or slowly. Useful information, but limited. Up close, in conversation, you learn what they actually think, what they know, details that a glance from across the room could never reveal. Imaging gives you the view from across the room. Brightness in a few broad colors, enough to make an educated guess about what kind of object you are looking at. Spectroscopy is the conversation. A detailed breakdown of exactly which wavelengths of light a source is emitting or absorbing, and in what amounts, which can reveal its composition, its motion, its age, and, crucially for objects like the MIDIS red sources, whether its light is dominated by starlight, by dust-reprocessed starlight, or by the distinctive emission of material falling into a black hole. For a candidate red source from MIDIs, spectroscopy can do several things imaging cannot. It can pin down the redshift precisely, rather than estimating it from broad colors. It can detect the specific spectral signatures of dust absorption, distinguishing a genuinely dust-obscured galaxy from one that merely appears red due to its distance and the limitations of the imaging filters used. It can detect the specific spectral signatures associated with stellar population age. Particular absorption features in a galaxy's spectrum become stronger or weaker depending on how long ago its stars formed, allowing researchers to estimate not just that a population looks evolved, but roughly by how much. And it can detect the specific emission line signatures of an actively accreting black hole, distinguishing that scenario from both of the others. The MIDI's red population, taken as a whole, has not yet received this kind of source-by-source spectroscopic follow-up at the scale of the full sample of over 100 objects. The survey paper itself is explicitly an early results paper, describing the survey and its initial findings, flagging this population as worthy of further study, rather than presenting a final interpretation for every source. The targeted follow-up on the most extreme subsample, discussed above, represents an early step in that direction, but the broader populate ion remains, as of this telling, the open frontier. Given everything described, there are roughly 3 ways to interpret what the MIDI's red population means, and where it fits into the broader pattern of early universe surprises JWST has produced. The first, more conservative reading, treats this primarily as a selection effect story, rather than a fundamental challenge to galaxy formation models. In this view, the MIDI's results mainly demonstrate that previous surveys, limited to visible and near-infrared wavelengths, were systematically missing a population of dusty galaxies that exist across a range of redshifts, including some relatively nearby ones, not exclusively at the very highest redshifts. Once these objects are properly characterized with follow-up spectroscopy, in this view, most of them will turn out to be consistent with existing models, simply galaxies that happen to be dust-obscured and therefore underrepresented in earlier catalogs, rather than evidence that the early universe as a whole was unexpectedly mature. There is good reason to think this conservative reading will explain at least some of the population. Dust obscuration is not a phenomenon unique to the early universe. Galaxies at all cosmic times can be dust obscured, and a survey that is newly sensitive to dust reddened light might simply be finding ordinary dusty galaxies at a range of distances, some of which happen to be at high redshift and some of which do not. Distinguishing "this is a dusty galaxy at redshift 2" from "this is a dusty galaxy at redshift 8" is itself a task for the kind of spectroscopic follow-up discussed earlier, and it is entirely possible, likely, even, that the more than 100 red sources found by MIDIs span a wide range of redshifts, with only a subset of them actually sitting in the highest redshift, most cosmologically interesting range. The second, more central reading, treats this as another genuine data point in the broader early universe maturity puzzle, alongside the massive early galaxy candidates, the little red dots, and other JWST findings of the past few years. In this view, any single object's classification remains uncertain. Pending spectroscopy, the cumulative weight of these findings, across different fields, different survey teams, and now, different wavelength ranges, suggests that galaxy formation in at least some regions during the first billion years was genuinely more efficient at producing dust, heavy elements, and evolved stellar populations than the standard models, calibrated primarily on more nearby, better understood galaxies, originally predicted. This does not require abandoning the standard cosmological framework, but it does mean the detailed astrophysics of how the first galaxies formed and evolved needs updating in places. The third, more expansive reading connects this specifically to the question of completeness itself, treating MIDIs less as a result about these particular sources and more as a demonstration of method. In this view, the most important outcome of MIDIs is not any specific source it found, but the proof that returning to an already exhaustively studied field with a new wavelength capability can reveal an entire hidden population. If this is true for the Hubble Ultra Deep Field, arguably the most studied patch of sky in existence, it is plausible that it holds for other deep fields surveyed primarily in visible and near-infrared light, suggesting that our current census of the early universe, across all fields, may be missing comparable populations elsewhere, simply waiting for the right instrument to be pointed at the right wavelength for long enough. All three readings agree on the observational facts. They differ in how much weight to place on this result as evidence for a broader pattern versus as an interesting but largely self-contained finding about one survey's methodology. That disagreement, is not confusion. It is the normal state of a result that is recent enough that the follow-up work needed to settle it has not yet been fully done. What is not in question, across any of these readings, is that a field many astronomers considered close to fully catalogued turned out not to be, and that the specific population revealed by looking again, in a new wavelength, fits a pattern that JWST keeps producing across the early universe. Evidence that things out there got complicated, in at least some places, faster than the simplest stories suggested. Let's come back to where we started. A patch of sky that astronomers had already photographed for over a week, already catalogued for 2 decades, turned out to contain roughly 500 sources that the most famous image of that patch of sky never showed. By now, the shape of the answer should feel different than a simple Webb found more galaxies. What Webb found was a population that existed in a part of the light spectrum the previous survey simply could not access, and within that population, more than 100 sources whose colors point toward dust, evolved stars, active black holes, or some mixture, sitting across a range of relatively early cosmic times. When results like this circulate, they tend to compress into one of 2 simplified versions, and both versions miss the part that actually matters. The first, simplified version, is the pure spectacle framing, a beautiful new image, more galaxies than ever before, presented mainly as a visual achievement. This is not wrong. The image is genuinely remarkable, but it skips past the actual scientific content entirely. The number 500 becomes just a big, impressive number, rather than what it actually represents. A previously invisible population in a field considered exhaustively studied. The second simplified version overcorrects in the other direction, treating any older than expected, or more mature than expected, finding from JWST as evidence that cosmology itself is in crisis, that the Big Bang model is collapsing, that everything we thought we knew is wrong. This framing has attached itself to several JWST early universe results over the past few years, and it consistently overstates what the underlying papers actually claim. The MIDI's paper does not claim cosmology is broken. It claims, carefully, that a population of red sources exists, that their colors are suggestive of dust, age, or in some cases something else, and that this surpassed the team's pre-flight expectations for what the survey would find. That is a meaningfully different, and more interesting, claim. What gets missed in both framings is the completeness story. The idea that one of the most studied regions of sky in existence still had an entire population hiding in it, accessible only through a wavelength range that simply had not been used there before at this depth. That is the part of this result that should change how astronomers, and the rest of us, think about every other deep field ever taken. If the pattern holds, and a field this well studied could hide a population like this, the implications extend well beyond the Hubble ultra-deep field itself. The most direct implication is for other deep fields. JWST has already conducted deep surveys of multiple other regions of sky, each optimized in different ways, some for area, some for depth, some for specific wavelength ranges. The MIDI's approach, an extremely long single-filter, mid-infrared exposure of a field already well characterized at other wavelengths, has not been applied to most of these other fields at comparable depth. If the hidden population found in the ultra-deep field reflects something more general about how dust, evolved stars, and active black holes are distributed in the early universe, rather than something specific to this one patch of sky, similar surveys of other fields could reveal comparable populations. It is worth considering why other fields might, or might not, show the same thing. Different deep fields were chosen for different reasons, and some of those reasons could plausibly affect how many dusty, or black hole-dominated sources they contain. A field D chosen specifically because it contains a known galaxy cluster, for instance, might be expected to have an overdensity of evolved galaxies compared to a field chosen for being as empty and unremarkable as possible, like the original ultra-deep field. F yield, with a different orientation relative to the plane of our own galaxy, might have different amounts of foreground dust from the Milky Way itself, which can complicate the interpretation of faint, red, distant sources. None of this means the MIDI's result S are not generalizable, but it does mean that the next step is not simply repeat this exact survey somewhere else and expect an identical number, but rather repeat this kind of survey across a range of different fields, chosen for different reasons. ND, see how the numbers and properties of these red sources vary, which would itself be valuable information about how representative any single field, including the ultra-deep field, actually is. There is also a broader idea under discussion within the astronomical community. The case for a genuinely new, dedicated deep field, one that would push JWST observing time on a single field well beyond even the MIDI's approach, potentially approaching or exceeding the kind of multi-week total exposure that produced Hubble's extreme deep field, but using JWST full suite of instruments and wavelength coverage from the start. Proponents of this idea argue that each time astronomy has pushed to a genuinely new depth, or a genuinely new wavelength range on a well-chosen field, it has revealed populations that were not just fainter versions of what was already known, but categorically new, exactly the pattern MIDI's just demonstrated again. A dedicated JWST deep field of this kind would represent a substantial investment of the telescope time that could otherwise be used across hundreds of other observing programs, studying everything from nearby exoplanets to individual stars in our own galaxy to other distant galaxies. The case for spending that time on a single, extremely deep field rests on exactly the kind of result MIDI's produced. The demonstration that depth and wavelength coverage, applied to a single well-chosen patch of sky, can reveal entire populations that targeted, shallower surveys of many different fields would simply miss, because those populations are individually too faint to detect, except in the deepest possible exposures. For the specific question of early universe maturity, dust, and evolved stellar populations versus active black holes. The path forward is more spectroscopy, on more candidates, across more fields, building up a large enough sample that statistical pattern NS, rather than individual unusual objects, can be used to test and refine models of how quickly the first galaxies formed, enriched themselves with heavy elements, grew central black holes, and began to look, in some cases, more developed than their age would comfortably allow. Here is the part of this story worth sitting with. For 2 decades, the Hubble Ultra Deep Field stood as a kind of monument, not just to what telescopes could do, but to a sense of having arrived somewhere, of having taken the picture, of a question. What is in this patch of sky? Having been answered as completely as the technology of the time allowed. It was reproduced everywhere, specifically, because it felt close to definitive. Nearly 10,000 galaxies, in a patch of apparently empty sky. It was never the final word. It was the word available in the wavelengths accessible at the time. It is worth being honest, too, about a temptation that comes with stories like this one. The temptation to reach for the single biggest, most dramatic sounding number available, even when that number does not actually belong to the result being described. The genuinely remarkable record holders for the most distant, earliest galaxies ever observed, objects whose light has been traveling for somewhere close to the full 13.8 billion year age of the universe, are real, and they are extraordinary. But they come from different surveys, different instruments, and in most cases different patches of sky entirely. Identified through targeted searches and confirmed through dedicated spectroscopic campaigns, not through the MIDI's imaging survey described in this video. Attaching that kind of record-breaking figure to the MIDI's result would be a disservice to what MIDI's actually found, not because MIDI's is any less interesting, but because what MIDI's actually demonstrated, an entire hidden population sitting unnoticed in the most famous deep field ever taken, is a different, and in some ways more broadly significant, kind of story than we found the single oldest thing. It is a story about how much we still do not know about places we already thought we knew completely, and that story does not need an inflated headline to be worth telling. When Webb returned to the ultra-deep field, it did not need to travel anywhere new. It did not need a new patch of sky, a new target, a new direction to point. It needed only a part of the spectrum that had not been used there before, applied for long in new GH, and an entire second population, substantial in its own right, was sitting there, unchanged, the whole time, simply outside the range of what anyone had been able to see. This is the actual revelation. Not any single source, not even the intriguing red population and what it might mean for early galaxy formation, but the demonstration that we have already looked at this, and we have already seen everything here, are not the same statement, and that the gap between them can be substantial, even in the most famous, most studied image in the history of the field. There is one more thread connected to all of this that deserves its own telling. Among the populations JWST has found scattered across these deep fields, the little red dots we discussed, some of the most compact, most intensely red sources at these distances, turned out, on closer inspection of at least some of them, not to be galaxies full of dust or evolved stars at all, but something else. Something actively feeding, growing, and shining by an entirely different mechanism than starlight. What they are, how many of them might be hiding in fields just like this one, and what they imply about how quickly the largest black holes in the universe manage to grow, is one of the strangest threads JWST has pulled on so far. That is a story for another time. We started with an image that millions of people have seen, the Hubble Ultra Deep Field, a patch of apparently empty sky that turned out to contain nearly 10,000 galaxies. Presented for 2 decades as one of astronomy's defining achievements. Then, we followed Webb back to that exact same patch of sky, with an instrument tuned to a part of the spectrum nobody had used there before at this depth, and found that the defining achievement had a second layer underneath it the whole time. Roughly 250 more sources. More than 100 of them red in a way that points toward dust, evolved stars, active black holes, or some combination. Sitting across a range of some of the earlier moments in cosmic history we can study. Not a contradiction of what came before, an addition to it, and a reminder that addition, at this frontier, can mean an entire hidden population, sitting in plain sight, in the most studied image we have. We do not yet know, for most of the MIDI's red population, whether dust, an evolved stellar population, an active black hole, or some combination, is the correct explanation for any individual source. That requires spectroscopy that has not yet been completed at scale for this sample. We do not yet know how representative this population is of the early universe as a whole, versus something specific to this field. Though, the broader pattern across other JWST surveys suggests this is unlikely to be entirely unique to this one patch of SKY. We do not yet know whether a dedicated, even deeper JWST field, the kind some astronomers are now advocating for, will be approved and carried out, or what it might reveal if it is. And we do not yet have a settled picture of exactly how galaxy formation models need to be adjusted to account for the cumulative weight of these early universe surprises. This one included. Though, the direction of the adjustment, toward faster, earlier, more efficient early structure formation in at least some regions, seems to be a consistent thread across multiple independent results. First, complete is always relative to the tools you had when you made the claim. The ultra-deep field was complete by the standards of visible and near-infrared imaging in the early 2000s. It was never complete in any absolute sense, and no survey ever is. Second, the most significant discoveries are not always about finding something in a new place. Sometimes they are about finding something new in the same place, just by changing how you look. This second point is worth connecting back to the broader project of this channel, because it applies well beyond deep field astronomy. Many of the most striking results covered in past videos, the discovery of water bound into Earth's deep mantle, the reanalysis of decades-old radio data revealing repeating fast radio bursts, the identification of unexpected molecules in the plumes of icy moons, share this same underlying structure. None of these required traveling somewhere new. Each required someone to apply a new technique, a new instrument, or simply a new question, to data, or to a location that had, in some sense, already been looked at. The frontier of discovery is not always at the edge of what we can reach. Sometimes it is sitting in an archive, or in a patch of sky already photographed, waiting for the right combination of capability and curiosity to reveal what was there all along. Third, a color, on its own, is a clue, not an answer. Red can mean dust. It can mean an evolved stellar population. It can mean an active black hole. The MIDI's survey found the clue. The answer requires follow-up that has only just begun. Fourth, patterns across independent results carry more weight than any single result, however striking. The MIDI's red population matters partly on its own terms, and partly because it joins a growing list of early universe findings, several of which point in a similar direction. Fifth, the next major discovery in a field like this one might not require a new destination at all. It might simply require returning to somewhere already familiar, with a capability that did not exist the last time anyone looked. If one of the most thoroughly studied images in the history of astronomy was still missing an entire population of sources, what does that suggest about how confident we should be in calling any survey of anything complete? When a finding like this gets compressed into a headline, what gets lost? And what would it take for coverage of results like this to convey both the genuine excitement and the genuine uncertainty at the same time? And on a broader level, how many other things, not just in astronomy, do we consider fully examined, fully understood, simply because nobody has yet had a reason or a new enough tool to look again? If this one stuck with you, let us know which part landed hardest. The idea that the ultra-deep field had a hidden layer this whole time, the specific red sources and what they might turn out to be. Or the bigger question of what else, in places we think we already know, might still be waiting. And if you want more of these careful looks at what JWST actually found, not just what the headline implied, subscribe to Galaxy Pulse, and we will see you in the next one. Somewhere in a patch of sky, the size of a grain of sand, in an image taken more than 20 years ago, there was a second layer of the universe, waiting for someone to look again. It is worth ending on the broader shape of what this means for how astronomy proceeds from here. Webb did not need to discover a new object in the sky, point to it, and say, "There, that's new." It pointed at coordinates that have been published, and studied by thousands of researchers for 2 decades, and found that the coordinates themselves were not the limiting factor. The limiting factor was which part of the light arriving from those coordinates anyone had been equipped to detect. Every other deep field, every other catalog, every other complete survey carries the same implicit asterisk, complete, given the instruments available at the time it was made. As new instruments come online, not just Webb, but future observatories already being planned, designed around wavelength ranges and sensitivities that do not yet exist in any operating telescope. This same exercise, returning to old coordinates with new eyes, will likely keep happening, and will likely keep finding things. The Hubble ultra-deep field was the first place this happened at this scale, in this way, with this much existing data to compare against. It is unlikely to be the last. There is something almost reassuring in this, beyond the purely scientific interest. It means that the value of the data we have already collected, every deep field, every archived exposure, every catalog painstakingly assembled over decades, is not fixed at the moment it is collected. It grows, sometimes unpredictably, as new tools become available to look at it in new ways. The Hubble ultra-deep field data from 2003 and 2004 did not need to be redone, replaced, or corrected to make the MIDI's discovery possible. It needed only to still exist, carefully archived, waiting for an instrument that did not exist yet to be pointed at the same coordinates 2 decades later. In an era where new discoveries are often framed as requiring bigger telescopes, more distant targets, or entirely new missions, MIDIs is a reminder that some of the most significant discoveries left to make may already be sitting in datasets we have had for years. Not because anyone made a mistake the RST time, but because the question being asked of the data has changed, and the data, it turns out, had an answer all along.